Today we will see the reduction of quadratic form to canonical form. A homogeneous expression of the second degree in any number of variables is called a quadratic form. Suppose if A is equal to AHG, HBF, GFC, X is equal to XYZ and X transpose is equal to XYZ. Then X transpose AX is equal to AX square plus BY square plus CZ square plus 2FYZ plus 2GZX plus 2HXY, which is a quadratic form. Now, suppose if let lambda 1, lambda 2, lambda 3 be the eigenvalues of a matrix A. And we know how to calculate the corresponding eigenvectors for each eigenvalues. And let us take the three eigenvectors are x1, which is nothing but x1, x2, x1, x2, x3, and then y1 we can have see y1, y2, y3, and z1 we can have small z1, z2, z3. We can have the eigenvectors, the corresponding eigenvectors for three eigenvalues. So whenever we find the model matrix, which is a P transpose AP, if you want to find out the canonical form or sum of squares form or principal axis form, we have to find out P transpose AP, so that you will be getting the diagonal elements to be the eigenvalues, and the eigenvalues are in the diagonal elements and the rest of the elements are 0. Okay, so likewise we have to find out the quadratic form and which is reduced to the canonical form. So finally you will be getting as in the form lambda 1 x square plus lambda 2 y square plus lambda 3 is z square. And P is the matrix transformation, which is an orthogonal matrix. Now let us see how to find out the matrix corresponding to the quadratic form. So the quadratic form is ax square plus by square plus cz square plus 2fyz plus 2gzx plus 2hxy. So we know first of all we have to convert this quadratic form in the matrix form. So to write down the matrix form, we have to follow this procedure. The first entry is you have to write the coefficient of x square. The diagonal elements are the coefficient of x square, the coefficient of y square, and the coefficient of z square. So these are the diagonal elements. Then a12 is nothing but 1 by 2 coefficient of yz, and here also it is same, a12 is equal to a21. So a21 is also equal to coefficient of 1 by 2 of coefficient of yz. a13 is equal to a31. So a13 is 1 by 2 coefficient of zx, and this is same as a31. So 1 by 2 coefficient of zx, and a23, the second row, third column. So 1 by 2 of coefficient of xy, and this is same as a32, 1 by 2 coefficient of x1. Okay, so that is from the quadratic form. If you write, the first entry will be a and the second entry will be h, then a13 is 3. So a12 is same as a21, and the diagonal is b. Then actually diagonal is about a22. Then a23 is f, a32 also equal to f, a13 is g, so a31 is g. And then the diagonal A33 is A11 is A, coefficient of x square, coefficient of y square is A22, coefficient of z square is A33. So likewise, we have to convert the quadratic form into the matrix form. So this is the first step in order to reduce the quadratic form to canonical form. So first of all, we have to write down the matrix. Okay. Now let us see the problem. How to reduce the quadratic form. 3x square plus 5y square plus 3z square minus 2yz plus 2zx minus 2xy to canonical form. So the step one, the first step, we have to write down the matrix of the quadratic form. This is the given quadratic form. So let us write down by using the procedure, the matrix A. So the diagonal is nothing but the coefficient of x square, then coefficient of y square is A22, coefficient of z square is A33. And then 1 by 2 of yz. So 1 by 2 of yz is what? Minus 1. So this is same as A21. Then 1 by 2 of zx is the coefficient of zx is 2. So therefore you will be getting A13 is 1 and A31 is 1. And then the coefficient of xy is minus 2. So A23 is minus 1. A32 is also equal to minus 1. So this is the matrix A for the given quadratic form. Then you know how to write the characteristic equation. So the characteristic equation is lambda cube minus S1 lambda square, then my plus S2 lambda minus S3 is equal to 0. So you know how to find the S1, S2, S3. So S1 is nothing but the sum of the diagonal elements. So 3 plus 5 plus 3. So you'll be getting A plus 3, 11. And then S2 is equal to the sum of the principal matrix of the diagonal elements, the minor matrix of the corresponding principal diagonal. So adding that, you will be getting the value for S2. So S2 is 5 minus 1 minus 1 3, then plus for minus 1 you will be getting minus 1 minus 1, then 1 3, then plus for 3 3 minus 1 minus 1 5. So simplifying this you will be getting S2. So 15, then minus into minus you will be getting minus 1. Then plus minus 1 into 3, you will be getting minus 3, then plus 1, and then here 15 minus 1. Simplify this, 14, then minus 2 plus 14. So 28 minus 2, you will be getting 26. Then S3, you find out the determinant value. So determinant value of the given matrix. So the determinant value you have to find out for the given matrix. So 3 into 15 minus 1, then plus 1 into, leave the first row and second column, you will be getting minus 3, then plus 1. Then plus 1 into, leave the first row and third column, therefore you will be getting 1 minus 5. So this is 14. So 3 into 14, then minus 2, and then minus 4. So 42 minus 6, therefore we will be getting 36. So the equation, characteristic equation is lambda cube minus S1 is 11 lambda square, S2 is 26 lambda minus 36 equal to 0. Now using the synthetic division, if you solve the characteristic equation, you are getting the three different roots. So your lambda is equal to 236 as its eigen values. So solving the characteristic equation, you are getting the eigen values. Now next step, you have to find out the corresponding eigenvector for this three eigenvalues. The first case, you can take a lambda is equal to 2. So by taking lambda is equal to 2, you are getting the equation x minus y plus z is equal to 0. Then minus x plus 3y. Then minus z equal to 0. And x minus y plus z is equal to 0. So by using the cross multiplication method, you can see x by 1 is equal to y by 0, which is equal to z by minus 1. Therefore, the first eigenvector x1 is equal to 1, 0, minus 1. And you have to normalize this, the normalized form of x1. So the normalized form is, the normalized form for x1 is, the first value is 1, and you find out the square of 1 square and 0 square, then minus 1 the whole square. Therefore, 1 plus 1 you will be getting 2. So root 2, and 0 by root 2, then minus 1 by root 2. Okay. So actually it is nothing but 1 square plus 0 square plus minus 1 the whole square. So therefore you will be getting 1 plus 1, which is 2. So you have to write this is square root of. So the denominator is 1 by, the denominator is root 2. So each x1, each entry of x1 is divided by root 2. So that is the normalized form. Then similarly, corresponding for the next case, lambda is equal to 3. The eigenvectors is the same way. If you find, you will be getting the eigenvector as x2 1, 1, 1. So the its normalized form is, so the normalized form is, here you will be getting 1 by root 3, again 1 by root 3, 1 by root 3. So finally, third case, this is second case. Then case 3, by taking lambda is equal to 6, the eigenvector is x3 is 1 minus 2, 1. So its normalized form is, the normalized form you're getting it as 1 by root 6 minus 2 by root 6, then 1 by root 6. So you are getting the normalized form of each eigenvectors. Hence, we write down the model matrix. The model matrix is P is equal to, so the normalized form, the first x1 is the eigenvector, the normalized form of the eigenvector x1 is taken as a first column. So that entry is 1 by root 2, 0, minus 1 by root 2. Then the normalized form of x2 is taken as the second column. So 1 by root 3, then again 1 by root 3, then again 1 by root 3. Normalized form of x3 is taken as the third column. So 1 by root 6 minus 2 by root 6, then 1 by root 6. So this is the model matrix. Then we can find out the transpose of the model matrix. So you know how to find the transpose. The transpose is nothing but 1 by root 2, 0, minus 1 by root 2. Then second column can be written as second row. Then third column can be written as a third row, minus 2 by root 6, 1 by root 6. Okay. So in order to convert it to the canonical form, you have to find out P transpose AP. So you know what is P transpose. So write down P transpose. That is 1 by root 2, 0, minus 1 by root 2. Then 1 by root 3, 1 by root 3, 1 by root 3. Then 1 by root 6, minus 2 by root 6, 1 by root 6. Then into the given matrix A. A is what? 3, minus 1, 1, minus 1, 5, minus 1, then 1, minus 1, 3. Then you write a P. P P is nothing but 1 by root 2, 1 by root 3, 1 by root 6, then 0, 1 by root 3, minus 2 by root 6, then minus 1 by root 2, 1 by root 3, 1 by root 6. So when you find the product of these three matrix, you will be getting the eigenvalues to be the diagonal elements, and the rest of the elements are 0. So you are getting the diagonal matrix. Okay, so P transpose AP gives you the transformation. Now using this, we have to write down the quadratic form that reduces to the canonical form. So it is in the form X transpose AX, and therefore the finally hence the given quadratic form reduces to canonical form. So as Y transpose, and you know it is the diagonal elements, so you can write a D Y transpose dy. So Y transpose you can write y1, y2, y3, and diagonal matrix you can write 2 0 0 0 3 0 0 0 6. Then y is y1, y2, y3. So therefore the quadratic form you are getting to be from the quadratic form, it has been reduces to the canonical form. Just finding the product of this, you are going to get 2y1 square, then plus 3y2 square, then plus 6y3 square. So again I'll write here. So final form is Y transpose Y dy is equal to 2y1 square plus 3y2 square plus 6y3 square. So hence we have reduced the quadratic form to the canonical form by the orthogonal transformation. Thank you.